Can you hear me? People online? Can you hear me? Yes. Then let's start for one PDE seminar of the Dean of the University of Chile. Today, I have the pleasure to introduce the Professor Jarrín, nuestro invitado, that will talk to us from non-local to local Navier-Stokes equation. Thank you.
Okay. So first, thank you so much for the invitation and the introduction. I'm very happy to be here in Santiago. This is a joining work with Jeremy Lochamin. Actually, he's a Ecuadorian PhD student in University of Luxembourg. And as already said, today I will talk about from non-local to local Navier-Stokes equations. And it doesn't work. Okay. Okay, so here's the plan of my presentation. First, I will give you a little introduction to the Navier-Stokes equation. And then I will give a motivation of our study when we consider a non-local fractional term in these equations. And this non-local fractional term is actually given by the fractional Laplacian operator. So I will give you a definition and some properties of this nice operator.
Have a problem, sound problem.
Okay.
Can you please?
Okay.
Can you please hear?
Yep. Okay. Is better? It's better like this. Can you hear me?
Can you hear us? Can you hear me? Is it okay?
Puede ser el internet que tenga también el problema. Me voy a conectar de mi oficina para ir chequeando ya. Pero es una sola persona.
No, son dos.
Okay. Personas. Yeah.
Personas.
Okay.
Alonso. Alonso.
Okay. Can you hear me? Okay. Can you hear me? Is okay? Hello. Creo que sí se escuchaba, ¿no? Ah, ok.
Disculpe.
Con este mejor. ¿Con este se escucha mejor? Sí. Ahí se escucha. ¿No se escucha? Problemas técnicos. Creo que no, ajá, no escucho.
O es la conexión de ellos. No, la conexión de ellos, pero esos dos personas, probablemente es nuestra conexión.
Ah, ok.
No,
No importa. Suele pasar. Iba a conectarse en su compu.
Pero tenemos mi computadora y más dos.
Ahí se escucha. Aló, aló. ¿Se escucha algo? ¿Se escucha? No, no tampoco. Ok. Bueno. Eso es.
De horario y vamos a hacer we will do the reset of the server. Please 5 minutes to see if we can solve this problem, because
Okay.
without this we cannot record, because we cannot record the monitor, and we will lose the people who they are trying to reset the server. Sorry, guys.
Okay.
Otherwise, I took continue with the first. Who's online? Who is online?
We have three.
Can you have it?
We have.
Hasta eso, un cafecito.
Ah, okay.
Gracias.
What's a coffee, please?
No sé.
There is very important in this, which you want to participate. No, 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 bueno, hay que decir que el evento.
¿Puedes escribir en
Ah, sí.
negro, porfa?
Pero voy a ponle en el chat entonces.
Eso,
¿En eso?
eso, gracias.
Bueno, hay que mencionar que el evento es en homenaje a nuestro colega Mike. Sus 60 años. Reconocimiento. Y es que se considera. Podríamos hacer un sondeo de lo que estamos haciendo. Ya, mira. ¿Dónde sería bueno hacer una cena de la conferencia de Mike?
En el morado.
¿Qué?
En el morado. En el morado. ¿Cómo se llama? Morado. Morado.
Está Claudio, así que aprovecho de que los tengo los dos en la
No, pero tú eres experto en. Tú sabes hacer navigación. Muy bien. Yo solo conozco un restaurante, nada más. He visto bien, pero ya fuimos tantas veces que no. No, ahorita saben. Pero ¿no?
Ahí se escucha. Aló, aló. ¿Se escucha? Aló, aló. ¿No?
Si me estima la cantidad de gente, yo les puedo decir.
Necesitamos a la página de conexión. Ah, no.
Sí, yo creo que tiene que haber una diferencia.
No, con que tienes que
The
ser ahora
universal
un
flavor.
Universal, sí.
It's kind of.
¿Así? Never happened. Just today.
Yes. And
Right.
in the last. The only problem.
Yes,
with the
because.
internet. I think.
Oh, well, maybe it's that the internet is not good for this
The
game.
problem is that you cannot save your presentation.
Ah, okay.
without-
So it's here the problem. Right?
Yes, here is the problem.
So it's a local problem.
Pero el tema es
Siempre es muy buen restaurante.
en
¿Cómo se llama ese restaurante?
el año pasado estábamos eso que está en metro de Guadalajara.
Pero ahora sí que estoy al mercado, pero
Ok, ya hay que preguntar a la gente.
¿cómo se llama el restaurante?
Vamos a ver, vamos.
Lo de ¿cuál es los juegos?
Ah, gracias. Para los juegos.
Ah, ese otro. ¿Verdad? Pero este es súper bueno que hicimos el año pasado.
This formula here, where where we have two unknowns. First, we have the velocity of the fluid U and the pressure P. On the other hand, we have U0 is the initial data, which means the velocity at the time t equals to 0. Moreover, we have a viscosity constant, which is strictly positive. And in this talk, we shall assume that this is equal to 1, only for simplify the things. So it is well known that the Navier-Stokes equation is a relevant physical model for a large variety of studies, like oceanography and turbulence studies. However, the mathematical theory of these equations is not rich enough to prove the global well-posedness of solutions. And all the mathematical problems related to the Navier-Stokes equations are actually given by this nonlinear transport term in the equations. So the history is that nowadays we have two main theories to give a mathematical study of these equations. The first main theory was given by a French mathematician, Jean Loret, in 1834, who construct global with solutions. So what is the idea? If we take the equation and we multiply by the solution U, we formally get that solutions must verify this estimate here, which is called the energy control. And this estimate suggests that the solution must be bound in the time variable and with values in the space L2. And moreover, this other term suggests that the solution also belongs to this L2 local space in time and with values in this Sobolev space H1. So we can construct this kind of solutions, which are called weak Loret solutions to the Navier-Stokes equations. And the main idea is to regularize the nonlinear term by taking a convolution product in this part here with a nice function theta, which depends on epsilon. And then we recover a solution to the original problem when the parameter epsilon goes to 0. So we know the existence of these solutions. However, we don't know the uniqueness of the solutions, and also the regularity issue is a very hard open problem for this kind of weak Loret solutions. On the other hand, we have another important theory for constructing solutions to the Navier-Stokes equations, which was given by these Japanese mathematicians Fujita Kato in 1962. So the main idea is to consider the linear heat equation, which we have in this formula here. And then using the Fourier transform, we see that solutions to this equation write down in this formula here, which is called the integral formulation of the linear heat equation. And here, this convolution kernel, HT, is given explicitly by this formula, which is the well-known heat kernel. So getting back to the Navier-Stokes equation, the idea is to consider, to take first the divergence operator in the world equation, and using the divergence free condition on the velocity U. First, we can see that the pressure P is related to the velocity U by this equation. In other words, if we have the velocity U, we can recover the pressure P. And this fact allow us to introduce an operator, which is called the Lorenz projector, given by DSP, which is defined by the following formula. Is the identity minus, here we have a sum of these terms, where this term RE is given by the Riesz transforms defined by the derivative, the partial derivative, divided to the square of the fractional of the Laplacian. So with this formula and the Lorentz projector, actually we can get rid of the pressure term in the Navier-Stokes equations. So we can consider this nonlinear equation, which is somehow similar to the linear heat equation that we had here. And following this idea to construct solutions by using the integral formulation, we can actually look for solutions which solve this mild formulation to the Navier-Stokes equations. Here we have fixed point problem because the velocity u, or unknown, appears in both the right-hand side and the left-hand side of this equation. And moreover, what is the advantage to consider this kind of mild formulations to the Navier-Stokes equations? First, we can consider a large variety of functional spaces to look for these solutions. For example, the classical Lebesgue spaces, the Sobolev spaces. And moreover, we can consider another sophisticated functional spaces to construct solutions such as the Besov spaces, Lorentz, Morris spaces, etc. On the other hand, the main technical problem with this mild formulation is given that actually we obtain local in time solutions. In some cases, the solutions can be extended to global ones, and there are some smallness conditions on the initial data. But in all generality, we don't know if my solutions are or not global in time. And there are also a lot of blow-up problems associated to this part. Okay, this was a very, very fast introduction to the Navier-Stokes equation. And then we will motivate our study, consider the non-local Navier-Stokes equation. So the idea is to substitute the classical Laplacian term by this fractional version with where this operator denotes the fractional Laplacian operator. And I will give you a precise definition and some properties of this nice operator. And from the practical experimental point of view, the main motivation to consider this equation is given by some studies in anomalous turbulence diffusion problems. So the idea is that this term give us a better compression of these anomalous turbulence problems. And moreover, also for the numerical point of view, there are some studies that suggest that fractional solutions behaves in some scenes as the classical one when the parameter alpha is sufficiently close to 2. So this is our main motivation to our study. And actually, we want to give a rigorous framework to understand what happens when the fractional Laplacian operator goes to the classical one in the setting of the Navier-Stokes equation. So for this, I will introduce the fractional Laplacian operator. And our starting point is to recall the classical Laplacian operator, which is given by this well-known formula here. Actually, this is a second order derivative operator, which is also an homogeneous operator of the two. Moreover, if we see the action of this operator in the Fourier variable, we see that this two-order derivative in the variable space becomes a multiplication by the sample here in the Fourier variable, which is the norm of C to the square. And following this idea, we can define a fractional version of this operator. So the idea is very simple. If we want to derive alpha times in the Fourier variable, actually we multiply by the norm of this vector to the power alpha. This is the easy way to define a fractional derivative operator. Of course, we have a definition in the spatial variable, which is given by this expression here, where PDE means the principal value actually is given by this limit here. And if we see this formula, we can see that this is a non-local operator in the sense that here we consider an integral in the whole space. And for this reason, this talk is called the non-local to local transition because the fractional Laplacian operator is a non-local operator. And we want to move to the classical one, which is a local operator. Oh, sorry. So also we have a homogeneity for this operator. This is an operator of order alpha, since we have this formula here. Okay, so with these ideas in mind, we can go to the main part of this talk to study this non-local to local transition. So we get back to the fractional Navier-Stokes equation given in this formula here. And the idea is that for each value of the parameter alpha in the fractional Laplacian operator, we get a corresponding fractional Navier-Stokes equation. And we have a corresponding solution, which is denoted by U alpha. So we want to understand what happens, what is the asymptotic behavior of these solutions when the parameter alpha goes to 2. And for this, intuitively, we see that if in these equations we take the value alpha equals to 2, then we recover the classical Navier-Stokes equation, the local version of this equation. And we are interested in develop a rigorous framework to study this convergence from the fractional case to the classical one when the parameter alpha goes to. This is the main idea of this talk. Okay. So for this, we have to give a better understanding of the existence of my solutions. We are working with my solutions. So if we consider the initial value problem from the generalized Navier-Stokes equation, I mean generalized because here we consider both the non-Lacan problem and the Lacan problem. This my formulation for these equations is actually given by this formula here, where this convolution kernel is the heat kernel in the local case when alpha is equals to 2, and is defined by the inverse Fourier transform on this function here in the non-local case when the parameter alpha is smaller than 2. So the first thing to do is to construct. Yes, of course.
Yeah. So you have this local problem, Navier-Stokes local equation, but I suppose that if you start with not projected Navier-Stokes.
Actually, this is
and then you replace Laplacian by the non-local operator.
Yeah.
You will not get this when you project, or will you?
No, actually, this is the projected problem. You mean for this term, for the Lorenz projector?
What you did is you project it first, and then you replace Laplacian
Yes,
by local.
yes, in this.
Yeah, but you can do it the other way around. You can first replace
Okay.
Laplacian, and then you project.
Yeah, you can do in this way because there are. I think you get the same result if you first take the fractional Laplacian operator and then you apply the Lorenz projector.
But how can the
because it could mute. Yes, because you always have the divergence free condition on the velocity in both the fractional case and the classical one. Yes, it can mute. It can mute. You can see in the Fourier variable. It commutes. Okay, so we have here this my formulation. Oops. Okay, and the first thing to do is to construct these my solutions to our generalized problem. So for this, as already said, yes, dime.
Vuelve a concepto. Supone que el alfa es una velocidad
Sí.
y una
Físicamente hablando, tiene que ver con, es una difusión, un fluido con difusión anómala. El Laplaciano viene a representar la difusión del fluido y digamos, esta es una difusión rara en el sentido de que tiene un orden fraccionario de derivación.
Sí, entiendo eso, pero la dimensionalidad de la ecuación como la regla, que porque es como derivada fraccionaria, entonces hay la viscosidad y es diferente.
Sí, sí, aquí la constante de la viscosidad, bueno, acá no se ve explícitamente porque desde el inicio tomamos igual a 1, pero para que la dimensión física esté acorde, la constante de la viscosidad también va a variar, digamos, con el parámetro alfa.
Ya es algo diferente.
Algo diferente. Ajá, es una viscosidad diferente, que depende del alfa. No, en este caso, por eso siempre vale 1. Siempre vale 1, se puede generalizar al caso en donde la viscosidad dependa del alfa y pedir que esa constante se comporte bien, digamos, respecto al alfa. Okay. So we are here in the existence of this my solution. So we take the parameter alpha larger than 1 and smaller or equals than 2. We shall work in the framework of Sobolev spaces where the regularity parameter S must be larger than 3/2. So if we take an initial data belonging to this Sobolev space, actually we can an existence which is given explicitly in this formula here, and we can construct my solution to the generalized problem given in this formula here. Okay. Here in this, actually, this is not the main result. This is somehow standard result in the Navier-Stokes theory. And the main remark in this result is that we need to consider a higher regularity order because the parameter S is larger than 3/2. Actually, in the classical Navier-Stokes theory, we can construct mild solutions in the setting of Sobolev spaces when the parameter S is larger or equals to 1/2. But for technical reasons, we have to consider a higher regularity result. Another important remark is that we can see in this explicit expression for the existence time T alpha, this is a positive time as long as the parameter alpha is larger than 1. So this fact justifies this technical constraint given here by on the parameter alpha. Okay, so what is the main idea? We shall consider a family of initial data in the fractional case when alpha is smaller than 2. And we consider U alpha the corresponding solution given by the previous proposition. Sorry. Moreover, in the local case, we have considered an initial data and U2 the corresponding arising solution. So we shall assume that the family of initial data in the fractional case converge to the initial data in the classical case in the strong topology of the space HS. And this fact is actually very important for us because it allows us to find a time t0 which does not depend on such that we have the lower bound here. I mean, if we suppose this convergence here, actually, we know that the whole family of fractional solutions are at least well-defined up to the time t0 here. Moreover, as we work in the sublevel space where S is larger than 3/2, then we have this classical ambient in the L infinity space. So we are able to prove a uniform convergence for the family of solutions associated to the fractional problem. And now we have the main result of this talk. So the idea is to understand, actually to measure how fast the fractional solutions move to the classical one. And to do this, we shall assume an initial convergence rate, which is given for the initial data. We shall assume that the convergence, the initial data converges to the classical one with this convergence rate given by the parameter gamma here. And with this, and with the time t0 introduced before, we can prove the following estimate for the difference of the solution in the fractional problem and the classical one. And here we have an interesting phenomenological effect, since we see that the convergence rate of solutions is not the same as the convergence rate assumed for the initial data. Precisely, we have the convergence rate of solution is given by a competition between these two quantities here. So if the parameter gamma is smaller than 1, we have that the maximum between these two quantities is given by the first one. And in this case, solution converge with the main velocity as the initial data. But if the parameter gamma is larger than 1, we have that the maximum between these two quantities is given by the second one. And then we have that solutions does not follow the convergence assumed for the initial data. And actually, we have here a smaller convergence. So to explain this phenomenological effect, I will give you a few ideas of the proof of the result. So we will consider both my formulations in the classical case and the fractional one. And our key tool is to study first the convergence of the fractional convolution kernel to the heat kernel in the classical case. For this, we have the following technical results. We have this convergence with an optimal convergence rate given by the expression minus alpha. And this optimal convergence rate will only explain the upper bound. The idea is to use the classical definition of sublevel spaces by using the Fourier transform. And then we define a function which depends of the parameter alpha given by this formula here, which is actually this sample here in this expression. And we can compute the derivative of this function respect to alpha. And by the mean value problem, actually, we have this convergence rate for the fractional kernel to the classical one. So with this key estimate, we get back and we study the difference between the fractional solution and a classical one. Actually, we consider first the linear part and the more difficult non-linear part in our equations. For the linear part, we actually recover the convergence rate that we have found for solutions. Here we clearly see that This term gives us this first convergence rate, which is given by the assumption on the initial data. And the second term gives us this second expression here, which is given by the convergence rate of the convolution currents. The nonlinear terms are always the most difficult to treat. So I only write down the formula, but this is not so easy to do. And finally, we have this convergence rate given in the statement of this result. What? Here? Actually, the idea is to compute the derivative with respect to the parameter alpha, where the variable t and the variable c are fixed, and we just consider functions depending on alpha, and we compute is the derivative. Okay. So this uniform convergence in the L-infinity space allows us to prove another convergence in the LP space. So we have a similar result where the convergence rate is also given by the parameter Q in definition of the LQ space in the spatial variable. So we have some final comments. These results can be done in the two-dimensional case of the Navier-Stokes equation when the regularity constraint is larger than 3/2, can be relaxed to we consider is larger than 1. This is only a technical requirement. And moreover, we can generalize this kind of results to another relevant couplet systems in the fluid mechanics, as the MHD equation and the Bussiness systems, for example. So in the future work, we aim to prove this convergence in strong topologies than the L-infinity. For instance, in the strong topology of the space HAs or the space, the solar space WSP, when the parameter P is equal to 2. Yeah. Sorry, I can.
Like stronger LP, but instead of using another.
No, I mean because this is I mean that the Solis space and V's in the L-infinity space. So actually, we prove our results in this space here, and it's not so easy due to some properties of the Fourier transform. So it's not so easy to do this part. In particular, in the case where P is different to 2. Another idea is to, in all this work, we have considered the my formulations of Navier-Stokes equations. But if we look for this type of convergence results for the weak low resolutions, we cannot use this idea. So this is here we need to find a very different approach. And moreover, we're also interested in study this type of convergence for the elliptic case of the stationary Navier-Stokes equation. I mean when the velocity U only depends on the spatial variable X. So these are very, very difficult frameworks, and we have to find new ideas to study this kind of convergence. Okay, so this is the reference, and okay, so thank you so much for your time.
Thank you, Oscar, for your presentation. Does anyone have any question or comment?
So thank you again for the presentation, Oscar. I'm very curious because I'm working in CFD in the part more computational,
Okay.
in the numerical part. Have you tried some numerical tests for the modifier fractional Laplacian with
No, actually, this is a theoretical work,
just
but we look for some numerical studies,
okay, so
which are also
are
very
you trying-
interesting too.
okay, because at the beginning you are
Yeah,
showing
we
something.
think that because in this part we don't know the optimality of these convergence, right?
Okay.
So maybe we can use some numerical studies to
Yeah, you need
to
more
study
robust-
these
more robust estimates for the numerical part.
Yeah.
Okay, thank you.
I have a question about, before there was a question about the physical meaning of the fractional Laplacian operator. But as I understand, the interest of studying it is that the asymptotical behavior of it approaches to the classic Laplacian. So
Yep.
studying this fractional Laplacian operator is more about having a easier way to approach the
classical.
behavior of the natural Laplacian Navier-Stokes equation.
Yeah, this is the idea. Actually, the fractional Laplacian operator is a good toy model to understand some very hard open questions in the classical case. So we have, for example, when the parameter alpha is large enough, actually we can prove the uniqueness of weak solutions, the regularity of weak solutions, which are very completely open problems in the classical case. Okay.
Thank you for the presentation. I have a question about anomalous diffusion that you have shown to us. Is there an evidence that it should be a fractional correction to the Laplacian, or what is the reason to introduce the fractional operator?
In our work, yeah, we have both motivations. First, we have some numerical experimental evidence which show that the fractional Laplacian operator is a good substitute for the classical one to understand the turbulence. And the second motivation is, as already said, from the theoretical point of view, to give a better understanding. Actually, the problem with Navier-Stokes equation is to understand the competition between the nonlinear transform term and the linear diffusion term. So there are some interesting studies with these anomalous diffusion term to understand this competition between these two terms in the equation. To understand how this competition between these two terms determines the dynamic properties of solutions.
May I ask another question?
Yes, of course.
It's about modeling. So it's related with the 6-Hilbert problem, which is to establish a hierarchy of equation when you change the physical scales. So typically you go from kinetic equation to diffusion equation or fluid equation, depending on the scaling you consider. For instance, you can get the Navier-Stokes equation as a limit case in the appropriate limit of the Boltzmann equation.
Oh yeah, this is a very interesting.
Concerning diffusion, it's even simpler. And usually when you take a certain parabolic scaling, you recover at the macroscopic level a diffusion equation with a diffusion coefficient which is proportional to the second moment of some local equilibrium. And then it becomes interesting when you don't have such a second moment because you have fat tails for the local equilibrium, then there is an appropriate limit in which you recover a fractional diffusion operator. So there is a work by Melet, Michler, and Moore about this. Is there a change that something can be done also for fluid limits?
I don't know. This is an interesting question, but actually I don't know.
I've never heard
So,
of this.
yeah.
So I have a simple question. You assume that T alpha is, I mean, you assume that you have that T alpha less than something, right? Imagine that T alpha is infinity. I mean, you have right to imagine that T alpha is infinity,
Okay.
okay? Maybe by doing the size of the initial data small enough, right? So can you prove the same kind of result if every T alpha is infinity?
If alpha goes to infinity,
Except
T alpha, yeah, I think you can prove. Actually, we can assume that we have a uniform control on the initial data, and with this local solution will become global in time, and I think we can iterate this kind of estimates here in the main result. Yeah, we can iterate kind of estimates, and here we will have maybe another constant dependent of a time t arbitrary large.
Okay, so you
So I think in the case of small initial data with a uniform control on alpha, we can prove that.
and if we go now in the opposite direction, I don't remember very well, but actually there is a sort of result by Natasha Pavlovich and Let's Katz probably. And they consider this a fractional Navier-Stokes, I think. Not probably not exactly the same, but similar. And they prove that you have blow up. Probably you need less dispersion, and then you have blow up.
You have blow up for smaller values, or
Yeah, probably I don't know, below 1.5 or whatever.
Yeah.
So in that same sense, do you have a way to say maybe okay, I assume that I have blow up for some alpha, and then I will stop having blow up for maybe a particular set of initial data?
yeah, a
That
very
way.
interesting question. Maybe yeah, we have a family. Maybe we have a family of solutions that converge to a solution with a blow-up phenomenon.
Maybe consider the same initial data that they take. What happens
Yeah, with
if you improve alpha? Yeah.
Thank you.
Another question or comment? Then let's say thanks again.
Thank you so much.